Hello everyone. In the discussion on solid state chemistry, our today's topic of discussion is X-ray crystallography and Bragg equation. Bragg equation is the theory on the basis of which X-ray crystallography is the tool which is used in order to find out or draw a conclusion about the size, shape and detailed information regarding the position of the atoms, ions, motifs, whatever in a crystal. So let's see how does it happen. First, X-ray is generated in an X-ray tube. This X-ray is then secondly filtered. Actually, when some metal is used, such as for example copper, it produces X-rays of different wavelengths. Now, what is the wavelength of X-ray? X-rays are actually the electromagnetic radiations of short wavelength of the order of 0.1 nanometer or 1 angstrom. Okay. Now, this wavelength is definitely comparable with the spacing of the atoms in the crystals. So, this characteristic X-ray is to be used for which the other X-rays, which are known as the white X-rays, those are to be absorbed. Such as in the visible range of light, we know white light is the combination or the mixture of light of different characteristic lights. So, in case of X-rays also, the wavelength of the X-ray may be having a various range. So all the X-ray of different wavelengths cannot be used. Only a monochromatic X-ray beam is required, which is known as the characteristic X-ray or the colored X-ray. That is why the higher energy or shorter wavelength X-rays, which are known as the white X-rays, those are to be absorbed by some filtering metals. So this X-ray is in the second step filtered, and the monochromatic X-ray is radiated or obtained from the after filtering. This monochromatic X-ray is then allowed to pass through the crystal. Then after interaction, the diffraction takes place. We would discuss what about the geometry of diffraction in the next slide. But before that, what happens? Let's have a whole view of the thing. Okay. So then this X-ray is allowed to fall on the X-ray plate. Then this type of patterns are obtained, or nowadays this type of graphical presentations are obtained in order to discuss the size, shape and detailed information regarding the position of the atoms in the crystals. Okay. So first of all, we have to start with the geometry of diffraction, or which is known as scattering. The nucleus of the atom on the lattice point does not interact with the X radiation due to its heavy mass. That means when X-ray is allowed to fall on an atom, then its nucleus is very massive, which cannot interact with the X-ray. But the electron, this is not so much massive in compared to the mass of the nucleus. So the electron around the nucleus actually interacts with the X-ray falling on it. Now the fact is that after interaction, the electron starts oscillating, and due to that oscillation, X radiation of the same wavelength comes out from that point. Thus an atom becomes a point source of X radiation. Now what about these lines? These lines, these parallel straight lines, are actually known as the wave fronts. Suppose the X-ray is started from here, okay, and the distance between these two lines is 1 lambda. That means it is completing one cycle of its wave from here up and down and here. Okay, so the phase of these 2 points are same. This point and this point, the phase is same. This point and this point, the phase is same. So on this, now if wavefronts of same phase interact with each other, then constructive interference takes place. Otherwise, destructive interference would occur. Okay. So now let us discuss about constructive interference and the order of diffraction. Okay. So the tangent of each wavefront produced from the lattice points undergo constructive interference. How? Let's have a look on this picture. So these are the wavefronts of the incident X-ray, and these are the lattice points. Okay, this is the lattice point, this is the lattice point, this is the lattice point. So after interaction, all the lattice points are radiating X-ray which have spherical wavefronts. Okay, this is the second sphere, this is the third sphere, this is the fourth sphere. Similarly, for this point, this is the first sphere, this is the second sphere, this is the third one, and so on. Now what happens, the tangent, suppose this line, this thin line is the tangent on the first wavefront of all the lattice points. Okay, what happens? And the phase on these points are same, so constructive interference would occur, and thus the most intense diffraction takes place. That means the constructive interference, due to constructive interference, the most intense diffraction takes place, which is known as the zero order diffraction. So the most intense zero order diffraction occurs from the interference of the first tangent of each lattice point. Now look at this diffraction. This is the first order diffraction. How does it come? It comes from this line, this line. Look at the movement of the cursor, this line. And how this line is obtained? Look, this is the tangent on the first sphere of this lattice point, while this is common with the tangent of the second sphere of this lattice point. The tangent of the third sphere of this lattice point, as well as the tangent of the fourth sphere of this lattice point. This way also a comparatively weaker interference, constructive interference takes place, and a weaker spot is also obtained here in this point in the X-ray photographic plate, and this is known as the first order reflection. Now I use the term reflection. Reflection must be quoted and unquoted with inverted commas, because this is not reflection, this is diffraction. But since we are selecting those diffracted rays which are similar to have been following the laws of reflection, that is why the term reflection is used. But whenever we write the term reflection, they must be enclosed by inverted commas. Okay, this way, after the first tangent, second tangent, third tangent interference, the first order reflection is obtained. Now the second order, what about the second order? Look, this is the second order reflection, and this is being obtained from this line. And what is the characteristics of this line? Look, this is common with the first tangent of this sphere, while third tangent of the next sphere. Okay, so 1 plus 3 plus 5, this type of similar phase interactions, that is constructive interference, are much weaker than zero or first order, but still a spot is obtained which is known as the second order reflection. Similarly, in the opposite direction, the minus first order or the minus second order reflections are also obtained. So the first tangent of one lattice point interferes with the second tangent of the next lattice point, third tangent of the further next lattice point, and so on. Thus the first order diffraction is obtained. Okay, now the Bragg equation. Okay, before the Bragg equation, we have to have some idea about the Bragg's spectrometer or the Bragg's law. Okay, so as I have said that the wavelength is comparable with the spacing of the atoms in the crystals. So let's have a look on the history first. So this idea actually, was absorbed by M. von Laue. He suggested that crystals can act as three-dimensional diffraction grating to X-rays. Okay, and he confirmed this. Actually, his idea was confirmed by means of experiment by two scientists, whose names are Friedrich and Knipping. Okay, so what did they do? They actually passed a beam of homogeneous X-ray, that is monochromatic X-ray. They passed it through probably some zinc blende. Okay, the crystals of zinc blende, and that resulted in they actually allowed to fall the diffracted rays on a photographic plate, and a definite diffraction pattern was obtained. So this pattern was firstly known as the Laue photograph or the Laue pattern, and from the Laue pattern it is possible to arrive at the detailed information about the atoms. Okay, and the important discovery that a crystal could behave as a three-dimensional diffraction going to X-ray, it actually led W.H. Bragg and W.L. Bragg, two scientists in the name of Bragg. So they used X-ray for the purpose of studying internal structure of crystal. Okay, so since a crystal may be regarded as consisting of large number of parallel and equidistant atomic planes, Bragg considered that the diffraction effects observed for X-ray could be represented as reflection of X-ray by successive planes of atoms in the crystal. Okay. Now the X-ray is generated in the X-ray tube. Here in the X-ray tube it is generated. Okay. It is passed through a series of slits to give a sharp and monochromatic beam. The beam is then directed. Where it is directed? It is directed to strike the face of a crystal. Here is the face of the crystal. Okay. This is the face of the crystal. Okay. Which is mounted on a graduated rotating tube. This is the graduated rotating tube. Now the rays reflected from the crystal are then allowed to pass through a detector known as the ionizing chamber, and this ionizing chamber is filled with the vapors of methyl bromide. Okay, this is the ionizing chamber. Okay. Now the chamber is rotated coaxially with the crystal table. The crystal table and the chamber are so adjusted that when the crystal rotates, this crystal is rotated. Okay. When the crystal is rotated, then through any angle, the crystal is rotated through any angle, the chamber rotates at twice. You know, when suppose when some reflector is rotated by theta angle, then its reflected ray is rotated by 2 theta angle, isn't it? So it is twice that angle, so that the reflected rays always enter the chamber. It has to enter this chamber. Okay. And the extent of ionization here, where the methyl bromide vapors are given, the extent of ionization produced by the reflected beam is measured by the electrometer. This is the electrometer. So this is about the Bragg X-ray spectrometer. Now the diffraction by powder method. This is another method which is known as the powder method. Here is the have a look of the picture where this is the glancing angle theta and here the 2 theta with the undifracted beam and the diffracted beam. So that is why 2 theta is plotted. Okay. Now this is a simple method. Okay. This method was developed by Debye and Scherer in the year 1916 and later by Hull, Hull in the year 1917. So instead of taking a single crystal in this method, finely powdered samples are taken. Okay, it is taken, actually this powder is taken in a thin walled glass capillary tube, and this glass capillary tube is irradiated by monochromatic beam of X-ray. Here, although in the picture crystal is written, but this is actually a set of crystals. Okay, where the randomly oriented planes in all possible directions are present. Okay, so the sample is considered to be equivalent to a large number of single crystal with all possible orientations. Out of this, some will be so oriented so as to satisfy the Bragg equation. So we shall talk about the Bragg equation right now. Okay, so this will satisfy the Bragg equation for a given set of planes. Another set of crystals will be oriented so that the Bragg condition is satisfied for another set of planes, and so on. This is the powder diffraction method, and this is the picture of the photographic plate. Okay, which is actually the X-ray plate. Okay, so that's why conical shape. These are the conical diffracted beam, and here when the X-ray it is allowed to pass through the X-ray plate, this type of spots are obtained. So they can be easily analyzed and have idea about the crystal. Okay. Now let us move on to the Bragg equation. So here I have used 3 to 4 slides for discussing the Bragg equation. Here this picture would be repeated in all the slides, but when you will take the note, then only one picture would be sufficient. Okay. Now, as I have said that when X-rays are incident on a crystal face, they penetrate into the crystal and they are scattered by the atoms or ions. So let's start. Let us consider a set of parallel and equidistant planes. This is a plane, this is another plane, this is another plane. Okay, they are parallel and equidistant planes. These are written by m, m dash, n, n dash, or so on. Okay, so these planes characterize the arrangement of the atoms or ions in the crystal, isn't it? So when a parallel beam of monochromatic X-ray, these two are parallel beam of monochromatic X-rays. This is the X-ray number X1 and this is the X-ray number X2. Okay, and they have the wavelength definitely lambda. Okay, so and this plane, the interplanar distance DHKL, is for our simplification written as D. Okay, so when a parallel beam of monochromatic X-rays of wavelength lambda strikes the planes m, m dash or n, n dash at some glancing angle theta, this is the glancing angle theta, this is the glancing angle theta. Okay, here one difference with the law of reflection: if you draw a normal, then the angle with the normal is called the angle of reflection or angle of incidence, but here it's reciprocal. Okay, that is 90 minus this angle, that is this angle, okay, which is known as theta and known as here the glancing angle. So at that angle it is striking the plane. So some of the rays will be reflected. Some of the rays will be reflected in this direction, x1 dash and x2 dash directions. Okay. Now this plane, m dash plane, will reflect in the x1 dash direction, and this x2 will reflect in the x2 dash direction. So when the rays reflected from successive layers in the phase, if these two reflected rays are in phase, then they will undergo constructive interference. So they have to have same phase difference, isn't it? So the condition for the constructive interference is that the path difference. Okay, the path difference. What is the path difference? I am calculating the path difference. So the path difference should be the integral multiple of wavelength lambda. Okay, so these 4 points are clear to all of you. Now move on to the next slide. As I have said, this picture is repeated, this diagram is repeated, but you need not draw this repeatedly. You just take these points. Okay, ignore this diagram for my convenience, or to make you understand. I am repeating the picture here. So the glancing angle theta. What is the glancing angle theta? This is the glancing angle theta. Okay, which is equal to x1 a m, also equal to x1 dash a m dash. This is theta. So this is written here. Now we have drawn two perpendiculars, AB on x2c and AD on x2 dash c. Okay. Now these two lines are also parallel. Therefore, easily it can be said that this angle is theta, because this angle is 90 degree. This is a right angle, so this is 90 minus theta. Again, this is a right angle, so this is 90 minus 90 minus theta. That is, this angle is theta. Okay, so angle CAD is equal to angle theta. Now path. What is the path traveled by x1 and path traveled by x2? The path traveled by x1 is what? x1a x1 dash. Okay, and this can be divided into two parts, x1a plus a x1 dash. On the other hand, the path traveled by x2 is x2c x2 dash. So this can be divided into four parts, x2b, bc plus cd plus dx2. Why you have divided into these parts? Because x2b is equal to x1a, while dx2 dash is equal to a x1 dash, isn't it? So they can cancel with each other, and only bc plus cd are left. And on the other hand, bc and cd are also equal, so only 2 bc or 2 cd can be written. So we move on to the next slide. So path difference. What is the path difference? The path covered by this minus the path covered by this. Okay, so x2 c2 dash minus x1 a x dash, x1 dash. So their difference is this: x2b dx2 dash, x1a and a x1 dash cancelling each other, so only left bc plus cd. Now bc equals to cd, so this is 2 cd. Okay, cd. Now this angle is theta. this is the perpendicular. So this right angle is ADC is the right angle. So what is the hypotenuse? Hypotenuse is AC. So this is nothing but AC into sine theta, isn't it? CD is AC sine theta, because CD by AC equal to sine theta. So CD equal to AC sine theta. So if it is 2 CD, then then it would be 2 AC sine theta. And what is equal to AC? AC is nothing but DHKL. For our simplification, it is written as DH. So it is 2D sine theta. So the condition for constructive interference is obtained. Now what is written here? It is considered that the path travelled by x1 up to A is equal to, that means why we have cancelled this with this. Okay, these 2 points are mentioned here. So you must also mention these points. Why we have cancelled x1A with x2B and AX1 dash with DX2 dash. Okay, these are written. I am just reading it once again. Path travelled by x1 up to A is equal to the path travelled by x2 up to B, and number 2, path travelled by x1 from A to x1 dash is equal to the path travelled by x2 from D to x2 dash. Okay, and finally the slide in what is once again here. You need not draw it. So wavelength of X-ray is lambda. Okay, the reflected, look, I have written the term enclosed by inverted commas. Okay, so you would also do the same. The reflected rays would undergo constructive interference on the condition. What is the condition? As I have said, that the path difference should be equal to the integral multiple of lambda. That means n, if m is some integer, okay, that is, it is 1, 2, 3, 4, etc., then 2d sine theta must be equal to n lambda. That is, the condition is n lambda equals to 2d sine theta. So this relationship is known as the Bragg's equation. Okay, and n is known as the order of reflection. Look, it is not written here. So let me tell you. If n is 1, this is first order reflection. N is 2, it is second order reflection, and so on. So by using this equation, we can easily calculate the interplanar distance, the density of some solid substance, or etc., etc. So in my next class, I am going to discuss some numerical problems on Bragg equation. Actually not in next class. Before that, I have to discuss the solid defects. Okay, defects in solids. So after having completed the defects in solids, and also I have to discuss, as you have in your syllabus, the structures of potassium chloride and sodium chloride. Those things will be discussed in my next class. Afterwards, we shall discuss the numerical problems. Okay, so that's all for today. Thank you. Have a nice day.